Okay, the topic of today's lecture is recurrent neural network, RNN. We learned about feed-forward neural network, we learned about convolutional neural network, and this is the third structure or third type of models. Basically, we have three main types of neural network, and we have learned about two of them, and this is the third one. So RNN is useful when you have sequential data. So far, data that we dealt with was sort of IID. We had a picture, you wanted to, decide about the class of this picture, the classification. So this picture has nothing to do with this picture. The fact that this is a cat has nothing to do that this one is a dog. They're independent. But sometimes you have a sequence of data. The nature of the problem in hand is temporal. So to make a decision, you need to know what happened in the past. Okay. For example, in language, I tell you, forget about neural network. I tell you, I went to a school. Okay, predict the next word. So the next word cannot be tomorrow. I can't say I went to school tomorrow, but could be yesterday, right? Could be last week. So basically, you can assign some sort of probability. All of the words don't have the same probability. You have some sort of predictive power by knowing what happened in this sequence. By knowing the sequence of words, you can say something about the future, or at least assign some sort of probability over the word that may come now. And there are many cases with many scenarios that you have this type of nature. You're predicting a stock price. It's important to know what happened in the past in a stock. In any type of time series, it's important to know what happened over the time. In robotics, you're taking pictures. You're designing a model for self-driving car. It's not just the image that you're observing at the moment. It is the images that you have observed so far. So the nature of the problem is temporal, and you have to deal with this temporal data. So the main model that we use in neural network to handle this type of scenarios, this type of problems, are called RNN. And RNN, like other main models in neural network, is not new. The RNN, in fact, has been introduced in 1986. It's quite an old method. Something important in temporal data is that the length of the input is not always the same. So far, the length of input was same in feed-forward and convolutional neural network. But that's not the case in temporal. I may tell you that I went to a school. That's my input. I went to a school, so I have 4 words. Or I may give you a sentence which has 10 words or 20 words, and I want you to predict the next word. So the length of your input might be different. That's a challenge. That's a problem. So the idea to handle this, or the intuition to handle this, is that suppose that I have a feed-forward neural network, and this feed-forward neural network can take one word and predict something for me. And there's another neural network which can take one word and predict something for me. And if I have a sentence of 2 words, let's have 2 of these networks. And if I have a sentence of 10 words, let's have 10 of these networks. Okay? So have this intuition in mind. But now the problem is that it doesn't handle the temporal nature, It doesn't capture what happened in the past if I have independent networks. Somehow I have to make a connection between them. The first intuition is that just have many networks for many words. But now make some sort of connection between them such that this network has some sort of information about the other network and knows what happened for the previous word and so on and so forth, okay? So to make this type of connection, let's connect the hidden space of this network to the hidden space of this network, okay? These are two feed-forward neural networks. Make a connection between hidden space of this network to the hidden space of this network. So I fit this network with I. I fit this network with went, okay? But when I say went, went goes to the hidden space, but this hidden space is going to be affected by this hidden space as well. And this hidden space knows about the first word, which was I, okay? So this leads to a structure which we call it RNNs, RNN. Each of these part is one of these feed-forward. This is the input to the unit. This is the hidden space, and this is the output. See? Input, hidden space, output. Input, hidden space, output. And as I said, we would like to make a connection between these hidden space. So make the connection between this hidden space and the next, the network, the hidden space of the next network. So we had weight from input to the hidden space, and we had weight from hidden space from the output. I need to define some sort of new type of weights, which are weights between one hidden space and another hidden space. Okay, this is basically RNN. And you can imagine that I have many copies of these network, which take care of the length of my basically input. Okay. So that's the idea. This idea is basically an instance of more general idea that has been around that has nothing to do necessarily with neural network, dynamic systems. You know, if you have temporal nature, the way to go about temporal nature usually is dynamic system. In dynamic systems, you have some states, and each state is a function of the previous state. Okay, so usually in many dynamic systems we have some sort of Markovian assumption, in the sense that we assume that this state is independent from this state. State t plus 1 is independent from state t minus 1, given a state t. So given, current make independence between past and future. If you tell me what's happening now, I don't care what happened in the past. You know, I can predict the future. You know, if I go for a job interview, they're going to ask me, what was your thesis? What was your publication? You know, which problem you worked on. They usually don't ask me, how was your GPA in elementary school, right? Because assumption is that what happened in the past, what happened in elementary school, definitely it has some sort of effect on my PhD thesis, you know, what happened in my elementary school. But all of those effects are present at the moment, the current moment, you know. I don't need to know them. Actually, I'm lucky that they don't ask about elementary school. If they do, actually, yeah. So I was young when I went to elementary school, and I had really I struggled a lot with mathematics for a couple of years, you know, in elementary school. So I'm so happy that they don't ask about GPA in elementary school. In dynamic systems, usually we assume that there's a function which maps one state to another state with some parameter theta, but we assume that this function is the same function from state t to t plus 1 and from t plus 1 to t plus 2 and so on. If you assume that in a dynamic system this function will change over time, usually you can't do anything, you can't predict. You know, you have to make some sort of assumption, restrict your model that the dynamic of the system doesn't change over time. Otherwise, it's going to be a very complicated system. So it is a dynamic system, but the dynamic of the system doesn't change over time. Okay, so this is constant. We have the same sort of assumption in RNN. So an extension of this dynamic system is when a state is not just a function of the previous state, but a state is a function of previous state and current observation. And each step there is a current observation which make a state. And you can think of this as, each state is a function of everything that has been observed from the past up to the moment, because, this st is a function of xt. But st is a function of st minus 1, and st minus 1 itself is a function of xt minus 1. And st minus 1 is a function of st minus 2, and st minus 2 itself was a function of xt minus 2. So st is a function of everything that has been observed from the beginning of the time up to the moment. Okay, but again, you have to assume that this g doesn't change over time. Otherwise, if this dynamic changes over time, it's going to be a very complicated model to work with. So this is basically the concept of parameter sharing. When we say that the dynamic doesn't change over time, it means that we have to share the parameters of, start with the original intuition that you have a network and you have another network and another network, and you make connection between the hidden space of this network. But you have to assume that the parameters of this network is the same as the parameter of this network, is the same as parameter of the next network. And the parameter between the hidden space of this network and this network is the same as the parameter of this one and the other one. So the dynamic of the model will not change over time. So to make sure that the dynamic will not change, we share the parameters of these networks. We can't change them from one state to another state. We can't learn, we can't generalize usually. So we come up, with all of these assumptions, we come up with this model. A dynamic system with some input and with some function, which is weight, which maps one state to another state. And we share them, we don't change them. W is same over the time, U is same over the time, V is same over the time. So again, each of them is one feed-forward neural network. So what we did in feed-forward neural network, so it was like some weights multiplied to the input. So let me show you with this one, which we have the formula for. Weights times the input, so U xt, right, makes this hidden space, but this hidden space is also affected by the previous state, so WST minus 1 will be added to this. You may add a bias to this, or you may not add a bias to this, as usual. And this makes the first part of this perceptron, this neuron. The neuron was just weighted sum of weights. And then we had to apply a nonlinearity to this. And this would be the nonlinearity. So I put tangent hyperbolic here because traditionally in RNN, they use tangent hyperbolic. We can use many other nonlinearity. In fact, it's not common to use tangent hyperbolic anymore. It's common to use ReLU now, these days. So you're going to apply nonlinearity to this, and that would be the output of this neuron. But the output of this neuron will be multiplied by a V, so V times ST, and you may add a bias to this, and it makes the output OT. Okay? And the output OT, if you want to interpret it as probability, as usual, you apply softmax to it, to make a probability vector. Any question about this? Yes?
How do people generally initialize their state vector?
They don't, actually. They initialize their weights, but we'll get to that. There are two ways, actually, to show, two type of diagrams to show RNN. One of them is this form. The other one is this form. So you may show it as a closed loop, or you may unfold it. Personally, I'm not a fan of this type of representation. To me, it's sort of misleading or confusing. So I like this one better. But anyway, you can see both of these two in the literature when they want to represent RNN. Yes?
Why are we multiplying the output of your nonlinear function with another weight? That is v.
So this is, if you have a feed-forward neural network, you have input, you go to a hidden space, right, through some weights. This weight is u here. From hidden space to output, you go with another set of weights. This is v, right? The only other thing that we have is that there's another network here, and hidden space of this network will be mapped to the hidden space of this one through W, right? Okay, so in feed-forward neural network and in convolutional neural network, we use backpropagation to learn weights. We can use backpropagation to learn weights here with some extension. It's called backpropagation through time, BPTT, backpropagation through time. So how backpropagation through time works? Okay, let's look at this and see how we can do backpropagation. There are W, there's V, there are U, that we have to take derivative of the cost function with respect to each of them. And it's going to be a little bit different from the backpropagation that we have seen before. Let's see what the difference is. Suppose that I have a cost function, and I call this cost function L. And this cost function L is basically summation of LT over time. So at each output step, OT, there is some sort of cost associated to this. My output is Y, so at time T, there's a cost. At time T plus 1, there's a cost. And in general, summation of all of these costs is my general cost, which I would like to minimize. Okay? So I have to be able to take derivative of this L with respect to all parameters of my model, which is W, V, and so on. But before I take derivative with respect to weights, let's see what would be the derivative of L with respect to nodes of my network. What would be the derivative of L with respect to OT? So any suggestion, how should I go for derivative of L with respect to OT? Yes?
Some of the derivatives, LT with respect to OT.
Sorry?
Just apply the definition from the first line and break it into a sum of derivatives.
Yeah. So yes, L is sum of LT. If I perturb LT, does it change it? It definitely change LT, right? If I perturb OT, it will change LT. Does it change anything else? Does it change LT plus 1 or LT minus 1? How does this change LT plus 1? LT plus 1. I just perturb OT. Definitely it has effect on LT because LT is, say, for example, output minus predicted output at time T. Does it have any effect on T plus 1? What type of effect?
Temporal effect, because it depends on what you said in the past.
Sorry?
Temporal effect, because you have to take the context into consideration. Like the previous part of the context of the sentence, the previous word of the sentence, then the subsequent word that you're talking, the T word.
Right.
And what the previous words have a bearing on what the next is going to come.
I mean, your example is valid if you're talking about input words. You're saying that my output has to do with previous words. That's correct. I'm not perturbing words. I'm perturbing output at time t. So the words comes into the model, some weights will be applied, some nonlinearity will be applied. At time t, I have an output. I perturb this output. It has no effect on time t plus 1. It's the output of the model. You know, it's not something inside the model. If I change something inside, yes, it does affect. But it's the output. Output, I perturb it, has no effect. Yes?
Can we do a chain rule and make it del L by del ST, and then del ST by del FT or something?
ST by ST. We can do chain rule, but I mean, as you mentioned, you know, we can use basically this definition and see that it only depends on LT, not anything else. In fact, if you want to use chain rule, it is L with respect to LT and LT with respect to OT, and you don't need to go over time because it doesn't affect, you know, any other time. But derivative of L with respect to LT is what? Sorry? It's 1, right? If I change, you know, LT, it doesn't change LT plus 1. It's just 1. And depends on the form of your cost function, you can take this derivative, you know. It is cross entropy, it's L2 norm, whatever it is. It has a form, it has a closed form which you can take derivative. You know, this output is a parameter of that cost function. Say, for example, it's OT minus OT prime, or OT hat squared. So you can take derivative of that. So it's okay. You know, this is 1, and this is okay. We can compute it. So we have no problem with taking derivative with respect to OT. But not all nodes are as easy as this one. You know, if I want to take derivative of L with respect to ST, or maybe let's start with capital T, and then T, capital T is end of the time. So I'm talking about the last unit. I'm talking about the last unit. Derivative of L with respect to ST. It's the last unit, so it doesn't have any effect on the unit after because there's no unit after that. You know, derivative of L with respect to ST, how do you write it? In terms of chain rule, yes.
Should just be some element of D.
Sorry?
Well, you would do chain rule through the output activation function, but then the heart of it would just be V. V is the derivative
V times?
times the derivative of L big T with respect to O big T.
Okay. Right. So basically, I understand your suggestion that this is basically a chain rule that L with respect to O capital T, when that's end of the time, and then O capital T times ST. And L with respect to OT, we can do, because we can do L with respect to any T. So that's okay. TOT with respect to ST, what is that? Sorry? It's just V. So it's okay to compute this derivative. But what about L with respect to ST if this T is one of the time steps, not end of the time? You know, if I perturb this ST, it's definitely going to affect OT, but it's going to affect ST plus 1 as well. And ST plus 1 will affect OT plus 1. Okay? So this chain rule is not as easy as this one. So basically, I can write it as, or you tell me, how can I write? Yes.
Same thing again.
I was going to say apply the original definition of L, but then the derivative of any LT where T is less than that T would be 0.
Okay.
And then individually compute the terms in the sum because it'll have a positive, a non-zero derivative with respect to any other T after little t.
You're right, but can you turn this description to mathematical notation and tell me what should I write here?
The sum from k equals little t to big T of the derivative of L sub k. with
K?
respect- Yeah, because k is the summation
Oh,
of x.
this K? Okay.
Yeah, with respect to ST. No, I think it's ST, because we want with respect to S, little t.
Okay. That's it?
Yeah.
Okay, so then how should I go about it now?
I guess you would apply chain rule for each LK with respect to little t,
Okay.
and that would be impacted through each of the ST after
Right.
little t.
Any T that it's gonna, any part that is gonna be affected by this. I mean, you're right that it doesn't have any effect on the previous T, and we have to take care of T and after. But I mean, let me just simplify this notation here. You know, I'm perturbing ST. ST has two types of effects. Effect on this direction and effect on this direction. Let's take care of effect of this direction first. You know, if I change ST, it's gonna change OT, right? So basically, I would say that if I change this ST, it's gonna change OT. So I will write this chain rule. But this is not the only effect of perturbing ST. If I perturb ST, it changes ST plus 1 as well. Okay, so to take care of that changes, I would say that it's going to change ST plus 1 times ST plus 1 over ST. And I have to do this over time, and definitely it's gonna be affected from T to the end of the time, not for the previous cases. Okay. So do you agree with this one? With this, what I have written here? So perturbing ST has two effects on this direction and that direction. On each direction, I just write. Okay. Yes.
So why are we moving in terms of t to t plus 1 and not from t to t minus 1? Because if you see that t plus 1, st plus 1 can be written in terms of st. So
No, it can be.
st is tan h of a of t, so b.
No, that's true, but think about what's happening in the network. What's happening in the network is that, you know, you change something here, a W will be applied to multiplied to this, and you get here. But if you change something here, you don't change ST minus 1.
Okay.
It's correct that you can compute mathematically ST minus 1 in terms of ST, but in practice, you don't go backward in the network, you know. You just apply the weight to this and go to the next step. You don't go to the previous step, right? So no, it doesn't have effect on the previous step. So I have summation over time, and the derivative of L with respect to OT is something that I can compute. So that's okay. Derivative of the OT with respect to ST is what? Is V. So that's okay. Derivative of L with respect to ST plus 1. That was the problem that we had here. I wanted to compute derivative of L with respect to ST. Now it depends on the derivative of L with respect to ST plus 1. That's where this word or this term, backpropagation through time, comes from. It's exactly the similar situation that we had in backpropagation. Backpropagation, I wanted to compute the gradient of one layer, and the gradient of one layer depends on the gradient of another layer. So the same thing happens if I call this delta t. This delta t depends on delta t plus 1. So t depends on t plus 1. But the good thing is that if I go to the end of the time, it's computable. So at time t, you have to know what's happening in time t plus 1. I don't know. But t time plus 1, t time plus 2, up to the end of the time, I know how to compute it. Now come back. So it's a recursive formula. It's over time, not over layers. Okay, so derivative of ST plus 1 with respect to ST. ST plus 1 with respect to ST. What is it? It was W if we had no nonlinearity. But we do have some nonlinearity. Sorry? You have to compute the derivative of that nonlinear function as well, right? And if you look at the classical literature about neural network, it is usually tangent hyperbolic. And if it's tangent hyperbolic, basically you have to take derivative. Your ST plus 1 is in fact WST plus UXT plus 1. Right? And then a nonlinearity, which is classically is tangent hyperbolic, should be applied to this. So if you want to take derivative of this one, for example, so you have tangent hyperbolic of u would be derivative of u, which is w, times derivative of this tangent hyperbolic, which is minus tangent hyperbolic squared. So it's 1 minus tangent hyperbolic squared of WST plus UXT plus 1. Okay. Yeah. So anyway, it's computable. You can do it. It's no problem. And okay, so it's a recursive formula, and then you go up to the end of the time, then you come back recursively and you compute every delta. So so we can take derivative with respect to O, we can take derivative with respect to S, we can take derivative with respect to we had only these two nodes. So now if I want to take derivative of L with respect to weights, V. So again, our general question, if I change V, if I perturb V, am I going to change only LT or I'm going to affect everything? Sorry? Only LT? Yes?
Should be everything.
Everything, because this V is shared, right? V is shared over time, over all of these step times. So if you change V, not only OT will change, everything will change. So this is basically summation over time of derivative of L with respect to OT and times derivative of OT with respect to V. But derivative of L with respect to OT, I know how to compute. Derivative of OT with respect to V is what? Sorry? It's just ST. So it's okay. I can take derivative of L with respect to V. I can take derivative of L with respect to W. So similar question, if I change W, one step will change or everything will change? Everything will change, right? So summation, I want to take derivative with respect to W, so if I take derivative with respect to W, you know, if I perturb W, ST will be affected, right? So it's derivative of L with respect to ST times derivative of ST with respect to W. Derivative of L with respect to ST, I know how to compute. It's recursive, but it's computable. So that's okay. Derivative of ST with respect to W.
ST minus 1 times 1 minus tan squared, whatever you do there. So
Exactly. You know, ST with respect to W, ST is basically W times ST minus 1 plus UXT, and in nonlinearity over that, which is tangent hyperbolic, it's computable, you know, you can compute. So that's okay. And you can take derivative with respect to any parameters that you have here, with respect to C, with respect to B. So the only problematic part was the derivative of L with respect to ST, which we can handle through this recursive function, and this is basically backpropagation through time. Okay? So it's okay. We can do that. But there are problems in, I mean, on paper we can do that. In practice, if you just write it, it's not going to work. And there are many reasons that it's not going to work, what we have written on paper and on the board. And one important problem is exploding gradient or vanishing gradient. We mentioned exploding gradient and vanishing gradient when we were talking about backpropagation and deep models, and I told you that the reason that people were not able to train deep models, basically in the past, was vanishing gradient, because in backpropagation, after a couple of layers, the gradient is going to be vanished. You know, the same thing is going to happen here. You can think of a deep network, or you can think of an RNN as a composition function. Composition function in a sense that it's a function of a function of a function of a function. So in neural network, you can think of each layer as a function, and the next layer is a function of that function. Or in RNN, you know, in each step you have a function, and the next step would be a function of that function. So it's a composition function. And gradient of composition function basically would be multiplication of gradient, right? So if you have f of g, means you have f of g of x, and you want to take derivative with respect to x, basically you have g prime of x times f prime of g of x, right? So it's g prime times f prime. So f of g would be f prime times g prime. So in general composition matrices, we can think of the derivative of a composition matrix of this form. So it's basically multiplication of derivatives together, okay, with this definition. Now see what's going to happen. You know, consider a very simple case. In this simple case, suppose that the derivative of each of these components is constant, it doesn't change, it's alpha. There are two cases, either this alpha is less than 1 or it's greater than 1. So, and you multiply this alpha capital T times. So it's alpha to the power of t. If alpha is less than 1, alpha to the power of t converges to 0 if alpha is less than 1, and converges to infinity if alpha is greater than 1, right? So basically, no matter what the alpha is, it's going to give you some sort of problem. Either it's going to explode or it's going to vanish. Means either it's going to be very large or it's going to be very small. And you might think that, okay, why should I care, but it's just gradient, it could be a very large number, it could be a very small number, I don't care about it. The thing is that there are some practical issues with respect to, is this a small or large values, A small values and very small values for gradient, vanishing gradient, means that you can't remember what happened in the past, because you want to backpropagate by this gradient, If after t iteration it goes to 0, it's negligible, means I forgot what happened at that time, I cannot backpropagate from that time. And suppose that, in natural language processing, I give you a long story, I tell you that when I came to Canada, I was in Toronto. I rented an apartment close to University of Toronto. After 10 months, I went to Montreal, and I stayed in Montreal for 2 years, and then I came to Waterloo. And in Waterloo, I did my PhD. And, I give you a long story, and then I ask you, my apartment in Toronto was in downtown or it wasn't in downtown? It was far from downtown. And you have a knowledge that University of Toronto is in downtown, and I told you that I rented an apartment close to University of Toronto. So you can, as a human being, you can conclude that it was downtown, right? But if you have a network and you feed all of these sequence to the network, by the time that I ask this question, you completely forgot what happened, about my story 10 years ago. So you won't be able to answer this question anymore because you totally forgot that. So this is basically the effect of vanishing gradient in RNN. And in exploding gradient that we are going to see with more details actually later on in this lecture, exploding gradient means that you have this search space, and in search space there's a large gradient. It's as if you have like sort of cliff in your search space, It's a sharp gradient. And then you have even a small step size that you go through toward, the direction which gradients suggest. And you have this cliff, and you just basically get to this cliff and will be shoot on the other side of the search space, You're pretty close to get to the mean, local mean, but you get to this and it will shoot you somewhere else, and then you have to search with a small step size again and again and again and again to come back here. But if this gradient is large, then it shoots you somewhere else again. So we're going to see this with slides in more details later on. But both of these two can cause problem, exploding gradient and vanishing gradient. Yes?
So the gradient is just essentially a vector which determines the direction in which we move our weights. Then can't we just normalize that and let the learning rate determine our step size? Or is there a problem with that?
No, it doesn't help if you normalize it. It doesn't help if you normalize this. We can see that there are some, if you relatively, change the value, it doesn't help. We can see that there are some techniques, basically some hacky techniques, which people use in training. And it doesn't basically involve normalizing, but it involves clipping the gradient, you know. They don't let it to go that far, which helps in practice, but it's not mathematically sound, you know. Okay. So how can we handle this problem? How can we handle the problem of vanishing gradient? And how can we handle the problem of exploding gradient? Over time, there has been many different ideas to handle this problem, and I'm going to mention a couple of those and see what we do at the end. I will tell you what we are doing at the moment to handle this problem. One idea was what is used to call historically echo-state network. And there is still, you know, some variations of echo-state network around. An echo-state network basically is based on the fact, you know, when I told you about gradient to be a constant, alpha, you know, it was the case that the gradient is scalar. You know, if the gradient is not a scalar, but is, I mean, it's a matrix, like you have a Jacobian matrix. If you have a Jacobian matrix, if you perturb S, you know, if you have changed delta S, suppose that you have decomposed this Jacobian matrix by singular value decomposition, for example, and there are some eigenvectors and some eigenvalues and some eigenvalues corresponding to some eigenvectors. These eigenvectors are different directions of search with this Jacobian suggests, and these eigenvalues are the importance of each of these directions. You know, if I go towards the direction which eigenvector V suggests, the amount of change would be lambda delta S if lambda is eigenvalue corresponding to that eigenvector. And you can see that the problem of vanishing and exploding will happen again. If this eigenvalue is less than 1, after t iteration, it will approach to 0. And if it's greater than 1, it's going to approach to 1. You know, one basically sort of ideal or sub-ideal case is that this value is close to 1. Okay, it's pretty close to 1. Maybe it's slightly less than 1. So yes, if it's alpha to the power of t, if t goes to infinity, still it will approach to 0, right? But t should be much larger to get to 0, right? Basically, if alpha is not way less than 1, so it gives me some time. I can still remember what happened 5 years ago, right? Compared to the case that alpha was so small, which I can't remember what happened 5 days ago. So one idea is to have some sort of contractive map. Contractive map means that choose W in a way that the eigenvector values of W are not much smaller than 1, slightly smaller than 1. One pretty interesting idea in echo-state network, which is recent, and they don't connect themselves to echo-state network, you know, because I mean they haven't realized that it's a variation of echo-state network, or they didn't mention that. But it is basically echo-state network. Is that, okay, you don't need to learn W. Just set W to identity matrix. And in practice, it works, you know, and you can think why it works. Because what W is supposed to do, W is supposed to give information about the past to the future, right? Even if it is identity, still you carry the information from the past to the future. Because your ST would be W ST minus 1 plus UXT, right? And then a nonlinearity will be applied to this. So still you have information about ST plus 1. This W is identity. So, you know, and you can see that basically ST plus 1 would be ST now, which this ST is just a function of ST minus 1 and XT. Right? Plus UXT plus 1. So in ST plus 1, I have observation of T plus 1 and the observation of T. And I have some information of T minus 1. So still I carry forward the information of what happened in the past when I want to compute something at the moment. Right? So I'm okay. So basically think about it intuitively this way, that, okay, given this state, you want to predict something about the future, put all responsibility for prediction on this weight from a state to the future, on V. Put everything on V. Okay? This state is just a summary of what happened in the past. Do whatever prediction you want to do with this. But it's additive summary. I just added the information from the past, give it to you. And now, whatever prediction you want to do, put the whole responsibility of the prediction to V. Now, this is echo state. There is another idea which is called long delays. Okay? And long delays, all of these ideas are hacky ideas, actually, that people have tried with experiencing with this network to train. So the idea is that, okay, so you don't want to forget the past, make a connection with longer than one step from the past to the present or to the future. So you said that ST minus 1 has direction to ST, and ST has direction to ST plus 1. So make a direct direction connection between ST plus 1 and ST minus 2. Right? So it delays this effect of forgetness, because when I do backpropagate, I not only backpropagate through this link, I do backpropagate through this link, And if derivative over this direct link has been vanished, still, I have some gradient here that hasn't been vanished yet, and I can backpropagate through that one and remember what happened in the past. The same idea, actually, the same intuition, has been used recently to have some sort of deeper structure. It's called residual network. And when residual network was published for the first time, was, a storm that, people can train a very, very deep model. But the intuition behind it is pretty similar to this old intuition of delayed or long delays connection between hidden nodes. Okay. So another idea is a leaky unit. Leaky unit actually is that between two states, between ST and ST minus 1, you are going to have a convex combination through a new parameters, tau. And what's going to happen here, if this tau goes to infinity, this is 1, and this is 0. Right? Sorry, this should be ST, not ST minus 1. So if tau goes to infinity, ST is just ST. But if tau goes to 0, then what's going to happen? This is if tau is 1, if tau is between, it can't be 0, it's between 1 and infinity. If it's infinity, it makes this 0, and it makes this 1 0. So this term will be cancelled, and we're going to have only this term. But if it's 1, this is going to be 0, and this is going to be 1, right? So 1 minus 1, 0, the first term will be cancelled, and we're going to only have the second term. So you make a linear combination. You know, in leaky node, you had a direct connection to t minus 2, for example, to t minus 3. Now imagine that you have a convex combination between t minus 2 and t minus 1, or between t minus 1 and t. And then you have a parameter tau. Then when you change this tau, your current state is either depends on the previous state, or it depends on the combination of these two states, right? So you have all sort of choices. Only this state, or between these two. But this tau is a new parameter of your model. You are not going to set it ahead of time. You deal with this tau as a new parameter of your model. So when you do backpropagation, you take derivative with respect to tau, and you backpropagate, and you learn it. What's the optimal? So basically, the idea is that in some cases, I may want the memory of the past to be around. You know, I need it. And in some cases, I may need to forget what happened in the past. And if you see here, actually, they do it with each element of S. You know, S is a vector. So tau is not a constant for the whole vector. It's a constant for one element of this vector. So I would like to keep this element of the vector around for a while, but I'm going to forget the second element of this vector. You know, think about hidden space S as the result of dimensionality reduction. You do PCA on data. You represent your data in a new space. Okay? Think of S as this new representation, because this is what exactly is, you know, a new representation of data. In PCA, for example, each direction of PCA is one direction of variation, you know. The first direction is thickness, the second direction is tilt, the third direction is tail, right? Something is important for you, something is not important for you. I don't care about tails. I do care about thickness. I care about the identity of this digit, you know. Some of these directions are important, some of them are not important. I would like to remember what happened in this direction in the past. I don't want to remember what happened in this direction in the past. So let the network decide about it. I have a new parameter will be learned through backpropagation, and they're going to decide which direction should be preserved and which direction should be forget. Yes?
So in your equation, where you have st minus 1 in the left term, should that also be indexed to the specific element?
Element of, yeah. I, yes. True. You know, example of the case that you need to forget something, or you don't need to remember in past. You know, I gave you an example that you do need to remember what happened in the past. You know, this story that I told you about being in Toronto and Montreal and so on. But sometimes this is my question. You know, I give you a sequence, and my question is that the number of A's that you have observed so far is odd or even. You don't need to remember what happened in the past. You know, you see the first A, and you set your counter to 1. You observe the second A, you set the counter 2. I don't care what happened in the past. You know, I don't care that I immediately saw another A, or I saw this A 200 steps before. It doesn't matter. Your question is that, is it odd or even? right? As soon as I set this counter, I don't care that when this happened. So in this case, it's okay to forget what happened in the past, right? But in some cases, it's not okay to forget what happened in the past. So let the network decide which should be forgotten, which shouldn't. Okay, so the solution that we really use in practice is gated network. And in a sense, gated network is sort of combination of all of these ideas from here and there, you know, that we have a leaky node and I have to forget this one and I have to remember this one and I have a parameter to forget this one, like tau. Let's put all of these together, and it's a model which is called gated network or gated RNN. And traditional gated RNN, which is built-in function in all of these packages, is LSTM, long short-term memory, which is quite old, 1997. Okay, there are many variations of this. So for so many times, people didn't work on neural network, but after deep network, actually, there has been many variations of LSTM. And the original author of LSTM recently, not recently, actually, a couple of years ago, had a survey paper about all of the variations of LSTM. And in his survey, there are 20 different variations of LSTM. From 1997 to 2000, I believe 13 or 14 that he published his paper, there has been 20 different variations of LSTM. After that, actually, some people, I will explain to you what LSTM is, but some people actually believe that LSTM is too flexible, you know. There are too many ways to forget and to remember and, you know, to discard this part or not discard this part. And maybe in practice, we don't need that much of flexibility. Let's make a simpler model, more restricted, gated model. And they came up with other type of models, which is called GRU, gated recurrent unit. These gated models are not still as popular as LSTM, you know, but there are many papers about that. These are some variations of recent variations of LSTM. GRU, gated recurrent unit, was published in 2014, and many follow-up papers after that, you know. So basically, if you go to literature, there are many different gated models, you know. But let me give you the general idea of this gated model. I'm going to start with GRU, which is more restricted compared to LSTM, and then we will see LSTM. Because the argument of people who publish GRU is that LSTM is too flexible. You don't need it. Let's make it restricted, and this is the restricted version. Usually people present LSTM or GRU with some, you know, pictures. And again, if you go to literatures, there are many different type of pictures. Personally, I was not able to make sense of any of these pictures, you know. And the fact that there are many different representations for each of these networks, I think, is you know, confirming that other people actually had the same feeling as me. So they look at this one and they was not able to make any sense of this the diagram, and they made another one, you know. And the next one was not able to make any. So it's overwhelming, you know. It's many different type of diagrams. It's pretty hard to make any sense of that. And I don't suggest that you look at these diagrams or make any sense out of that. Just go to formula and math. It's way more clear, you know. This diagram is supposed to tell you what's happening in this mathematical formula, but I think mathematical formula is more clear than this type of diagram. So in GRU, I'm using the notation of this 2014 paper. So the difference with what we have used so far, if hidden space in our notation was S, and nonlinearity was sigma. Nonlinearity in their paper is F, and hidden space is H. Okay, so just it's a notation of their paper if you want to look at the original paper. So new state T is a nonlinear function of previous state times W plus UXT. So we had this. Now let's define two new variables, ZT and RT. And ZT is WXT plus UHT minus 1, and RT is WXT plus UHT minus 1. But these W's and these U's are different W's and different U's and W's, okay? So W, when you want to calculate Z, is different from the W when you want to calculate R. These are just new set of weights that we didn't have before, and we do have it now. And then nonlinearity will be applied to this, and nonlinearity here is fixed. It's in their paper. The nonlinearity is sigmoid function, always. We don't change. So far, the only thing that we have done is to add two new variables, and definition of these two new variables. These new variables are called gate, and that's why these models are called gated models or gated network. Gate with the sense that it's like a gate which could be closed or which could be open. So basically you're going to let some information to flow or you're going to block it. So you open the gate or you close the gate. Depends on the situation that you want to forget something or you don't want to forget something. So this gate R is called reset gate. So by the name, it's clear that you're going to use this gate when you want to forget, right? Okay. Yes.
In the previous slide, are the U's and W's intentionally reversed, or
Sorry, can be.
are the W's and U's intentionally reversed? Because there, the U's usually go with X, and the W's go with the H.
Yeah, these are actually their notation that I'm using here.
Okay.
I mean, these are names, right? You can
Think of them other ways.
think of them the other ways. It's just a set of weights multiplied to this H, set of weights multiplied to this X. You know, this is not the previous W or previous X. Okay, so I have reset gate and I have update gate. So reset gate by name suggests that it's going to be used when I want to forget something. Now I'm going to define a dummy variable, which is my third new variable that I'm going to define, H tilde. And H tilde is tangent hyperbolic of WXT plus RT UHT minus 1. So the important part is this part, RT times UHT minus 1. This RT, the new variable that we define, is a vector, okay? And UHT minus 1 would be another vector. So HT minus 1 is HT minus 1 is the state at time t minus 1 multiplied by U. This notation means pairwise product. So pairwise product between vector R and vector UHT minus 1. So the first element will be multiplied to the first element. Second element will be multiplied to second element, and so on, so forth and so on, okay? So if this R is, for example, 0, you know, it's going to make UHT minus 1 0, you know, because it's going to be multiplied to this, so it's going to cancel this part. So if I set RT, or if I calculate RT, or if my model decides that RT is 0, for example, or some elements of that RT is 0, after this multiplication, corresponding element in HT minus 1 will be 0. So basically, I forget those. I reset those. Okay. But this is my dummy variable, ht tilde. My current state is a linear combination of the previous state and this h tilde. Okay, true update gate. An update gate, again, is a vector which basically element-wise can be multiplied to another vector and keep those or make them 0. So bottom line is that when you are looking at the current state, your current state is a linear combination of previous state and a function of previous state. And this function of previous state, t, has a component in it which can forget what happened in t minus 1. So I am at time t. Time t depends on t minus 1. This is t minus 1, not h minus 1. At time t depends on t minus 1 and a function of t. And this function of t has something which can tell me forget what happened in the past. Okay? Now all of these are new variables, new parameters to the model. Let model to decide about them. Let model to learn them. Okay? It's not intuitive at all that how they come up with this, This is basically a result of too many experiment with this type of networks and different type of needs that, okay, let's forget this, a good practice if you want to see what's happening here is to don't use any of these packages like Keras or TensorFlow or whatever. Just simply write a program for an RNN when the hidden unit is just a single unit. It's not a vector. So everything becomes a scalar now. These weights, W, whatever, becomes a scalar. And now it's very easy to see what's happening in practice, right? But how come they come up with this, configuration that let's multiply this by that one and forget this one? It's not intuitive at all. At least I have no intuition that there are many, many, many other ways that you can think of these combinations. And that's actually the reason that there are many variations of these gated networks, But through experiments, people realize that, okay, it's not a bad idea to have a dummy variable here or additional variable here, which led us to forget this one or keep that one. And yes, you had a question? Yes.
I wanted to know why we have the current input in the memory content, the new memory content, which we are ideally trying to forget. Want to forget some portion of it.
Sorry, what's your question again?
H tilde of t is equal to tan h of wxt plus rt into pairwise multiplication of uht minus 1. So this is basically trying to tell us that we want to retain some portion or we want to forget some portion of the past. So why are we having an input, the current input to this in that equation? That is your xt. Why is there an xt there?
This is, what is the definition of HT? Not in gated model, in general. The definition of HT is a function of a W. We had W, they have U. U of HT minus 1, what happened in the past, plus we had UXT, they have WXT. Plus what happened now, what's my observation? What's happened in the past plus my observation at the moment. Okay, now this is the standard definition of the current state, right? What they have here as addition is an RT, which let you to forget a portion of the past. right?
Okay. But
So
in the original equation, which is a ht is equal to zt into pairwise multiplication, so there we're trying to retain some portion of the past also because zt is your update gain, right?
you're talking about this one now?
Yeah.
I mean, is that clear why we are doing RT
It's
here?
like if you want to retain this, then the other one should be less. If this is more, that should
Okay, let's talk about these two separately. You know, up to this point, okay, up to this point, we have a standard definition of ht, which is a function of ht minus 1 and current observation, with the exception that I have a gate which block flow of the past in some directions. Okay? So we call this h tilde. This is my h tilde, right? Now, I would say that the current state is this either this h tilde that I currently calculated or ht minus 1. Right? If it's ht minus 1, means my current observation had no effect. If it's ht tilde, means, you know, I had a standard definition of the state with the exception that I forgotten a portion of them. These are the two extremes. Now take a convex combination of those. You could be in one of these two extremes. You could be somewhere in between, right? It's good to define or to invent some sort of reset or forget gate for the, not for neural network, for us, for human being. Reset or forget a portion of the past. Yes?
In the last equation, last line, ht, if I'm not mistaken, is a vector, whereas h tilde is a scalar, right?
Sorry?
ht,
No, h tilde also is a vector. But this vector, I mean, you can basically, you know, apply a nonlinearity to each element of the vector that you compute.
so that equation is element-wise, basically.
Yeah.
For every element ht.
Yes. Okay, have a nice long weekend and happy Thanksgiving. See you next week.